Hello, good morning. Let's start the lecture summary now. So today we are going to talk about the permutation group and Burnside's theorem. This will also be the last lecture for this course, where materials covered will appear in the exam. Next Tuesday, we will talk about something for fun, and then next Thursday, this time, we will give the solution of homework 6. Okay, so let's begin. Okay, consider a set of elements. Let's call it S. There are finite number of elements. We call this set of elements the ground set. And then we are very familiar with what is the meaning of a permutation. So a permutation is a one-to-one function from S onto itself. So for instance, this is the original permutation A, B, C, D, but then we can transform this permutation into another form, B, D, C, A, so we will see that this is a permutation. So a permutation here is one-to-one, and then so here we will see that each of these character A, B, C, D will appear here exactly once. So the meaning of this notation, actually, you can think of this as a function. So in this function, if you begin with A, then it will be mapped to B. So function of A becomes B, function of B becomes D, function of C becomes C, and function of D becomes A. So a permutation can be thought of as a special type of function. Notice that this notation does not specify the order of ABCD, so you can rearrange this ABCD in any way that you like, as long as the corresponding elements below will be corresponding to what we see here. For instance, ABCD with BDCA at the bottom is the same as if you start with DCBA at the top and then ACDB at the bottom. This is also the same function. Okay, suppose that the ground set S has n elements. We use A, big A, or sometimes with big A and a little sub n to denote all the possible permutations of S. So there are going to be n factorial of them. Now, because a permutation can be thought of as a function, so we can naturally use the binary operation, this dot, to represent the composition of two permutations. So here, this is an example. So we have some function f, and then a dot, and then a function g, f dot g. So what does that mean? So in terms of function, the ordering that we apply will be starting from the right and then on the left. So what will happen to A, B, C, D? So A, B, C, D, so for A, it will be first mapped to A, and then it becomes A. So after that, it will be mapped to B. So the composition of these two functions will map A to B. Is that okay? So for B, what will happen? So B will map to C, and then C will map to C, so B will map to C. And here C will map to B first, and then B will map to D later. So this C will be mapped to this D. C will be mapped to D. And finally, D mapped to D first, and then D mapped to A later. So D will be mapped to A. Is that okay? So if this is a permutation, this is another permutation. So we have a dot operator to denote the composition of these permutations. Now it turns out that this binary operation dot on the A, so this A is all the possible permutations, right? It is a closed operation. So if we begin with a permutation and another permutation, the resulting one will be also a permutation. Now the proof is rather easy, so you can verify this by yourself. And so this is just proof worth checking. So as long as we can see that in the end, in the resulting thing, each character is appearing exactly once. And also, this binary operation is also associative. What does that mean? It means that suppose that we have permutation pi 1, pi 2, and pi 3. And then suppose that we have pi 1 dot pi 2 operate first, and then dot pi 3. So this is a composition, right? So for this composition, it is applying pi 3, and then applying the composition of pi 1 and pi 2. So this is one way of doing so. The other is we do pi 2 and pi 3, the composition of this first, do something, and then operate on pi 1. So we will see that this binary operation is actually associative. So it doesn't matter we do these two combined first or we do these two combined first. So again, you can check why it is true by yourself. Now, we have a set A, all the possible permutations, and an operator, binary operator that is closed on it. So together, these two together will form some algebraic structure. And then we claim that it is actually a group. So how to show it is a group? So group needs four things. One is this operator is closed, and then this operator is associative, and then we have an identity element in this A. And then for each element of A, then it should have an inverse. Now, so we have done the first two parts, closed and associative. The identity is easy. The identity is just the identity permutation. So A map to A, B map to B, C map to D, C, D map to D. So for such a case, then no matter what permutations that you apply, then you apply the identity on the left or identity on the right, it will still give the same permutation as if unchanged. And then finally, for each permutation, there is an inverse. The inverse is just you exchange the rows. So for instance, let's see this one. The inverse of this one is you write BDCA at the top and ABCD at the bottom, right? Because applying this and then inverse subsequently, you will map everyone back to itself. So everyone has an inverse, there is an identity, so everything is verified. So this permutation set of all permutations with the binary operation and composition function, it is a group. So we can also define a permutation subgroup. So a permutation subgroup is just a subgroup of A dot. Okay, so this is called the permutation. So there is a subset of permutations G of A together with this binary operator. Together, it forms a group, then it is called a permutation subgroup. So recall that if we have considered all the permutations of A, B, C, D, there should be 4 factorial, which is 24 different items here. But here, G, it doesn't have 24 items. It has just 4 items. But we will see that for these 4 items, it is a permit. This is a group. So yeah, how do we check it is a group? Because it is finite. And then it is a subset of all the permutations. So for this one, we remember that there is a very easy way to check whether it is a subgroup. So we just need to check whether the operations is closed. Okay. So for this one, this is the identity. Identity applied on anyone will be back to the corresponding one. So this one multiply or operates on anyone is closed, is inside. And then this one multiply with this one. So A to B, B to B. So we will have A to B, B to A to A. We will have B to A, C to C, C to D. So we will see that somehow, if we operate this one on this one, then we will get something like this one. And then operate this one to this one, we will somehow get what? Get this one. And then this one is an inverse of itself, I guess. So everyone is an inverse of itself, and then you can see that after doing all the possible checkings, then this is closed, so this is a permutation subgroup. Okay. Yeah. So basically, what you can read these 4 items here is this one exchange AB, this one exchange CD, this one exchange both AB and CD. So if we apply this to itself, then it get back to the identity. Apply this one twice, we will get back to the identity. Apply this one twice, we will get back to the identity, right? Apply this one and then this one, it will, this one and this one, no matter in which order, it will get the last one because we are swapping AB and also DC. applying this one with this one, then we will be getting the first one, and then you can do all the checking. So this is going to be a subgroup. Okay. Now, why we want to study permutation group or permutation subgroup? Because it has some nice property that helps us solve some counting problem. Okay, so let's see. Okay, let's see how it will be related to a special form of counting problem. Now, first of all, based on a certain permutation subgroup, okay, we can use this subgroup to define whether two items in the ground set are related or not. So two items here, we say A and B from the original set, the ground set, is related. Okay, this is the ground set item. A and B is related if, for some permutation, A is mapped to B. So in the previous setting, so we are talking about this little ABCD, whether they are related or not. So we will see that A is related to B because for some permutation, A is mapped to B. Also, B is related to A because for some permutation, B is mapped to A. And then C is mapped to D, so C is related to D. D is also related to C. Is that okay? And then A is not related to C because there is no permutation such that A is mapped to C. Is that okay? So we have related or not. So somehow this related or not will be important to have some physical meaning that we want later. Okay, but before that, suppose that G dot is a permutation group. Then based on G dot, we can define a relation between the elements in the ground set. And then we claim that this relation is an equivalence relation. So the relation R, based on this G dot, is an equivalence relation. So to check whether it is equivalence relation, we need to check three things: whether it is reflexive, whether it is symmetric, and then whether it is transitive. So we want to have three things to check. So first of all, we claim that each item is related to itself because we want to, so to check this, we want to ask, is there a certain permutation that maps an item back to itself? Now the answer is yes, because the identity will give us a proof. So every item in the ground set is related to itself. Now the next one that we want to check is reflexive property. Excuse me. So suppose that A is related to B. Is it always true that B is related to A? So here it is using our wordings. So we are saying that suppose that some permutation maps A to B. Is there always a permutation that maps B to A? Now the answer is also yes, because for each permutation there is an inverse. So if such a permutation maps A to B, then the inverse must map B back to A. Is that okay? So because of this, then the relationship follows the symmetric property. And finally, transitive. So suppose that A maps to B and then B maps to C in some permutations. They need not be in the same permutation. As long as there is some permutation maps A to B and some permutation maps B to C. So is it true that there is always a permutation that maps A to C? Now the answer is also yes. Suppose that there is a permutation, let's call it pi 1, and in pi 1 A maps to B, and another permutation, let's call it pi 2 maps B to C. Then the composition pi 2 dot pi 1 will map A to C. And then pi 2 dot pi 1 is the application of two items that we choose in the set G with the operator dot. Because G dot is a group, it is closed, so that means that pi 2 dot pi 1 will be also an item of G. So that means that there is a permutation that maps A to C. Okay. So somehow, based on a permutation group or a permutation subgroup, so here actually permutation subgroup here, then naturally we can define an equivalence relation. So equivalence relation talks about things that which kinds of things will be considered equal, which kinds of things will be considered different. So equivalence relation is a way to help us to partition the original ground set into different groups. Okay. So what kind of counting problem can be used? I mean, can use this this idea to help us solve. So what we are going to show next is the Burnside Theorem. So forget about Burnside Theorem for now, because yeah, we will go back to here later. But here we are going to, the Burnside Theorem actually is a theorem that helps us to find out the number of groups or the number of equivalence classes that is defined based on the equivalence relation. So this may be complicated if you hear it now, but we will see that it is very useful and easy to apply with some examples. So let me start with some example first, and we get back to the meaning of this theorem. Okay. So we are going to look at, this is the first example counting problem that we are considering. So here, let's see this description. Suppose that we have an equilateral, and then there are 3 vertices. Each of the vertices here can be colored by one of the 5 colors. Let's say red, green, blue, orange, and yellow. Let's say there are 5 different colors that we can color the vertices. Now we are considering 2 colorings to be equivalent if after a rotation, then they become the same. So this one and this one will be the same because we can transform this one to this one by using a anti-clockwise 120 degrees rotation. Or this one and this one, they are equivalent because you can do one more 120 degree rotation, then we get from this one to this one. And the first one and the last one, they are also be the same because after rotations, we get the first one to become, sorry. So first of all, the first 2 are the same, but the last one is not. Because for the last one, no matter how you rotate, then it cannot be equal to the first 2. Okay, so I made a mistake, sorry. So in that case, only these 2, they are the same, and this one is not. Now, so altogether, how many possible colorings if we don't count things that are the same? So how many possible ways to color the triangle? So because there are 3 vertices on a triangle, and then each vertex we can color them in 5 colors. So that means that there are altogether 5 to the power 3 different colorings. But some colorings are considered to be the same because after rotation, if one can be mapped to the other, they are going to be the same. So we want to find out how many different distinct ways to color such that, such that all these ways are not considered to be the same. Now what we can do here is, okay, so let's get back to the permutation group and how we can apply things there. So in a permutation group, it is like a transformation, a permutation of these little ABCD. Now the ABCD that we are looking at here are, for each of these ABCD, it will represent one of the colorings. So we are going to look at ABCD such that there are going to be 5 to the power 3 different elements here, okay? So we are considering a ground set S that contains 5 to the power 3 different colorings to begin with. Okay, and then for this problem, we are going to define a corresponding permutation group such that by counting the equivalence classes, it will be the same as counting the number of distinct coloring. Okay, so what we are going to do, So we are going to have an item here that represents the identity mapping. So we have 5 to the power 3. Let's call it A1, A2, A3 up to A125. It maps back to itself as A1, A2, A3 up to A125. So there's a mapping there. And there will be also another one that corresponds to a rotation of 120 degrees. So for instance, if we have a case of red, red, red in the 3 vertices, after rotation of 120 degrees, it will still go to red, red, red. But then, if it is like the top is red and the bottom are 2 grids, red and green, then after a rotation of 120, maybe we are going to move the red to the right hand downward column. Okay, so it is going to map another item of red, green into something like green, red, green, something like this. So we will have another one that corresponds to the case of rotation by 120 degrees. And finally, there will be one more that corresponds to a rotation by 240 degrees. So in that case, to solve this problem, we are going to define a permutation group with ground set 125 items. And then in this permutation subgroup, there are going to be 3 items, 3 permutations. One corresponds to the identity, one corresponds to the rotation by 120 degrees, and one corresponds to the rotation by 240. And then we can see that what? So what is the meaning of an equivalence class? So an equivalence class contains all the elements in the ground set that are related. So when 2 things are related, what does that mean? It means that after some permutation, after some rotation, one configuration can be transformed into another one. So this is exactly what we want. Once we have defined the permutation group, and then we want to find out how many equivalence classes are there. So we will talk about how to apply Burnside and compute the number of equivalences classes later. Okay, so it's a little bit tricky here without the whiteboard. So if you do not understand what I'm talking about here, yeah, please go to the OCW recording to have more details. And then let's go to another problem. So this problem is, this time it is a square. And then each of the vertices, we can color it in one of the 7 colors. And then we consider 2 coloring to be the same if one can be obtained from the other by rotation. So for instance, this one and this one, so you rotate it by counterclockwise 90, you get this one into this one. And these 2 are the same, another 90 degree. And then these 2 are also the same. So we have actually these 4 colorings should be considered as the same way of coloring. Okay, so how many different colorings can we find? So again, what we are going to do here is we are considering a ground set with 7 to the power 4 elements, and then there are going to be 4 items in the permutation group. So we are looking at 4 permutations. Each permutation will be rearranging 7 to the power 4 items, and then we want to find out how many equivalence classes are there. So this is another problem. Okay, and also about this one, this time we are looking at a regular P polygon, and then each of the vertex can be colored in one of the 8 colors. So again, we look at the same type of problem. We consider 2 colorings to be equivalent if after a rotation they become the same. So in this case, the ground set will be how many items? The ground set will be P to the power 8 items, right? And then how many different rotations can we think of? So there are going to be exactly how many P different rotations that we can form, right? rotates by nothing, rotates by one vertex, rotates by two vertices, and so on and so forth, up to rotates by p minus one vertices. Is that okay? So we are going to form a permutation subgroup that has p permutations. And for each permutation, there are going to be p to the power a items. And then we want to find out the number of equivalence classes are there. Okay, so this is what we want. And then another problem. So, okay, so let me double check. Okay, so this is another problem. So this time we look at license plates. So license plates, 5-digit license plates. So they are all formed by numbers, decimal numbers. We consider two items to be the same if one can read the other in the same way from upside down. So for instance, suppose that 181, there is no pointer here. So 99861, after upside down reading, so you turn it upside down, you look at from the other side, it will become what? 19866. So 19866 and 99861, they are considered to be the same because if I mistakenly rotate this one upside down, it is like rotated by 180 degrees, then we get these two. But then these two are not the same. It is because it is just a reflection. It is not rotation by 180 degrees. Is that okay? So these two are not the same. And for some license plates, you can only view it in one direction, so you don't have any mistake. So we want to find out how many different license plates that we can form without any ambiguity. So in this example, we are looking at a ground set that contains 10 to the power 5 different items. So each one of them corresponds to a 5-digit number, starting from 00000 to 99999. And then in this example, we will have two permutations. Okay, one corresponds to what happens if we do not read things wrongly. So if we read things normally. So this is the identity permutation. And the other is what happens if the license plate is placed upside down. So in that case, some of them, you will, for instance, 99861, it will become 19866. But some of them, like 77777, even if it is placed upside down, it doesn't change. So it's still mapped to 77777 because if there is a 7 inside, then there is no way that you can mistakenly read it wrongly. So in that case, we will have another permutation that maps from A to B if A can be read as B from upside down. Okay. So in this case, we are given a permutation subgroup that has two permutations. We want to find out how many equivalence classes are there based on the original ground set item. Okay. Now, so all these problems corresponds to what? Defining a certain permutation group on a ground set and then count the number of equivalence classes in the ground set. Okay, so all of these problems are in this form. And Burnside tells us how we can do the counting. Okay, so this is Burnside Theorem. So let me write. So Burnside Theorem says the number of equivalence classes that R partitions S into can be found by this formula. Okay, so this formula has some new notation. So let me explain it. So we have psi of a permutation pi. It denotes the number of elements that are not changed under the permutation of pi. So we will have an example soon. So we call this the invariance, the number of invariant items in a certain permutation. Now, the number of equivalence classes, of course, we can count it by hand, but on the other hand, it is also easy to count it by looking at all the permutations in the subgroup of G dot, one by one, add up all the invariants, and then divide it by the number of items in G. So it is actually, you can think of this as the average number of invariants of a permutation. So for this one, let's take a look. Okay, so this is an example. So this example G has 1, 2, 3, 4 permutations, and then we want to find out the number of equivalence classes that A, B, C, D, the ground set is partitioned into. So we will see that there are exactly 2 of them, because A, B is one group. A can go to A can map to B. So AB is a group, and CD is another group. So there are 2 groups. Okay, so how can we get 2? So by Burnside Theorem, here we count the average number of invariants in this permutation. So for this one, there's 1, 2, 3, 4. So this is A map to A, B map to B, C map to C, D map to C. So there are 4 invariants here. And then for this one, A doesn't map to itself, B doesn't map to itself, but C maps, D maps, so there's 2 here, another 2 here, because for this one, A to A, B to B, so there's another 2, and for this one, it is 0. Okay, so 4, 2, 2, 0, so the average of them is equal to 2. So we can count the number of equivalence classes as 2. Okay, how we can prove it? Yeah, go to the OCW recording. Okay, so in this case, we can try to solve this problem by using Burnside. Okay. Now, for this problem, the ground set has 5 to the power 3 colorings. Okay, and then altogether we have 3 permutations to consider. One is rotation, one is the identity, right? One is rotation by 120, and one is rotation by 240. So for the identity, the number of invariants is easy. It is 5 to the power 3 because everyone is mapped to itself, 5 to the power 3. But rotation by 120, so we want an item such that after rotation by 120, it is still the same. So when can this happen? So this can only happen when all the vertices are colored in the same color. So you can have the case of red, red, red. Because for red, 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 after rotation by 120, it is still red, red, red. Is that okay? But if it is like red, green, blue, after rotation by 120, it becomes blue, red, green. So it is different from red, green, blue. So it is not the same, right? So if you want to have invariance after 120, it must be all the vertices, they are colored by the same color. So the number of invariant elements here is exactly 5, because there are 5 colorings that we can choose, so 5 of them. And similarly, rotation by 240, it is also 5. So the number of equivalence classes is the average number of invariants in the permutations. So it is 5 to the power 3 plus 5 plus 5, and then you add this up, divided by 3, so we get the answer 45. So Burnside will be very useful. So it transforms to counting the number of equivalence classes into counting the individual invariants in the permutations. Okay, so let's see another example. So here, let's see this example. So it is a square, and then each vertex has 7 colors. So altogether, there are 4 different permutations that we will look at. So this is 0 degree, 90 degree, 180, and 270. Now we need to be very careful in the counting now. So the number of invariants here, rotation by 0, is 7 to the power 4, because every ground set item is mapped to itself. So there are 7 to the power 4 of them. But if you want to have 90 degrees after rotation, you must have what? You must have all the vertices are colored in the same way. So it must be all reds, all greens, all blues, all yellow, whatever. So there are 7 colors that we can choose. So there are exactly 7 invariants here. Now, rotation by 180, it needs to be a little bit careful. It need not be all same color. Just opposite vertices are in the same color will be okay. So for instance, you can have red, green, red, green. It is okay. Again, red, green, red, green. Because after rotation by 180, you get red, green again. So in that sense, rotation by 180, you have 7 ways to choose the first color for this diagonal and 7 ways to choose the other vertices pair. So there are 7 square invariants we can form. And finally, 270 degrees, so there are 7 ways. So altogether, 7, 4 plus 7 plus 7 squared plus 7, you add all them and divide it by 4. So this is the number of equivalence classes using Burnside. And then another one. This time it is a polygon, a p prime number p-sided polygon. Now for this one, so we have p different permutations to consider. The identity permutation, there are p to the power a different invariants. But for all the remaining, because p is a prime number, you can easily check that in order to rotate by any number of vertices, when it remains to be the same, then it means that all the vertices has to be colored in the same color. So in that case, it's not p to the power, it's a to the power p, sorry. So we must have a to the power p, 8 is the number of colors for the first in identity, but for all the others, they're exactly a invariants. Is that okay? So altogether, they are a to the power p plus p minus 1 times a divided by p. These many different equivalence class. Now here, what does that mean? Here, it means that because this is a combinatorial argument, so this number is actually an integer. So it means that a to the power p plus p minus 1a is divisible by p. So we will have a to the power p must be equivalent to a modulo p. And then, because when a and p, they are coprime, then a to the power p minus 1 is equal to 1 modulo p. So here, this part assumes that a is coprime with p. So this is actually another proof for the Fermat's-Little theorem. Okay? Okay, another example. So here, 10 to the power 5, 5-digit numbers that we can form. So we have only 2 permutations to consider. The first one has 10 to the power 5 invariants, but then how about the second one? So how many invariants are there for the second one? So the number of invariants for the second one is equal to 10 to the power 5 minus the number of cases that are not invariant. So okay. So how many non-invariants are there so that we can count carefully? So here we claim that, so the first identity, they are 10 to the power 5, but the remaining, it is like this. So how do we count this one? Okay, so 10 to the power 5 minus 5 to the power 5, it is the case where, let me see. We want to count, we want to count the invariant, right? So, how can we get this one? So first of all, as long as the license plate contains 2, 3, 4, 5, 7, these 5 numbers, then they will be an invariant when we read upside down. Because when we read upside down, we won't make mistake, so we put it back. So it is an invariant. So how many of them? So as long as it contains 2, 3, 5, 4, 7. So as long as it is not the case that all of them are formed by the remaining numbers. The remaining numbers, there are 5 of them, 0, 1, 6, 8, 9. So as long as they are not those 5 to the power 5 numbers, then they are invariant. So altogether, the number of places or 5-digit number that contains 2, 3, 4, 5, or 7 is 10 to the power 5 minus 5 to the power 5. And then for the remaining part, they can also be invariant. Yeah, because some numbers, it is actually reading the same as if it is upside down. For instance, 10101. So although reading from upside down, it is still valid, but it is still the same as 10101. So how many such numbers are there? Now for such numbers, the middle digit has to be a 0, a 1, or an 8. Is that okay? So because if the middle digit is 6 or 9, then after upside down, then 6 change to 9, 9 change to 6, so it's not okay. So whenever the middle digit is 0, 1, 8, it is possible that it reads the same upside down. Now, if you want to read things upside down, the first digit must map to the last digit such that they are forming upside down pair. So if the first digit is 6, then the last digit must be 9. If the first digit is 1, the last digit must also be 1. So by fixing the first digit, we can then tell what the last digit should be for the license plate to read the same upside down. So there are 5 choices for what to choose for the first digit. And similarly, there are 5 choices for what to be chosen as the second digit. And then there are 3 choices for what to be chosen as the middle one. And then after these are fixed, there is 1 choice for the fourth one because the fourth one has to be equal to the second one, reading upside down. And there's only 1 choice for the fifth one. So altogether, there are 3 times 5 square of them. So this is a total invariant in these 2 different ways, 2 different permutations. Okay, so the average number of invariants, you divide this by 2, and this is the number here. Okay, so that's all for what I want to show today. And then if you really want to understand more, yeah, it is best to try an exercise. So we have assignment 6 ready, and then there are a few questions for you. Okay. Okay, yeah. I think that's all for today. So next Tuesday again, so I will prepare something for fun. So not that serious. So please, yeah, please come if you have time. And then for next Thursday, homework 6 solution. Okay. So thanks all for coming. Yeah, that's all for today. And then please go to the OCW recording to fill up the details of why Burnside theorem is correct. Okay? Thanks.